In this lecture, we are going to discuss the potential energy of a dipole in an external field. In the last lecture, I discussed about potential energy of a system of charges in an external field. In this lecture, I am going to discuss specifically the potential energy of a dipole. In an external field. Okay. So while discussing about torque acting on a dipole, we considered one diagram. Let us consider an external field having intensity E, and you are placing a dipole in that external field. Okay, this is your dipole. It is placed in the external field. This side is minus Q and this side is plus Q. It is making an angle theta with the field. Let it be the position. Now, in this case, we already discussed what is the torque acting, and we already have the equation in the first chapter. Torque is equal to P cross E, where P is the dipole moment, it is small letter p, and E is the electric field. P cross E is nothing but P sin theta. This we already discussed. Now imagine that with the presence of this external field, by the application of an external torque, your dipole is rotating. From its initial position, it is rotating and it is aligning at some other orientation by an angle d theta. Okay, initially it is at an angle theta. Now with the application of an external torque that is given by the external field, now your dipole is rotating by an angle d theta. So it is rotated by an angle d theta. Okay, initially it is at an angle theta. Now it is rotated by an angle d theta. For rotating this dipole, the external field must do some work, isn't it? The amount of work done will be stored as the potential energy. So let us calculate that work done. W is equal to integral tau d theta. Okay, where tau is the external torque, and let us consider that initially that theta is some theta 1, and after rotating d theta, now your dipole is at an angle theta 2. Okay, initially it is at theta 1, that theta, it can be theta 1. After rotating d theta, now it is at an angle theta 2. Okay, so you are actually rotating from theta 1 to theta 2. These are the limits. From where you got this equation? You already know from the 11th class physics. W is equal to integral f dx with the limits x1 to x2. When you apply a force F, external force, here in rotational physics, instead of F, it will be tau. Rotation force is called torque, and here you are not displacing by dx, but you are rotating. So displacement will be angular displacement. That's why dx is replaced with d theta and f is replaced with tau. That is how you are getting this equation. Okay, now you can substitute the values theta 1 to theta 2 what is tau external? It is given here. Tau external is equal to PE sin theta and d theta is there. So this is PE is constant, you can take it out, theta 1 to theta 2 sin theta d theta, isn't it? So what is it? PE into, what is integral sin theta d theta? That is minus cos theta. Integral of sin theta is minus cos theta, theta 1 to theta 2. So you got PE into minus cos theta, that minus you can take out, then minus PE cos theta, theta 1 to theta 2. Now let us give the limits. Minus PE into cos, what is the term here? Theta with limit theta 2 and theta 1. So upper limit minus lower limit. Cos theta 2 minus cos theta 1. Now since there is a negative sign here, you can rearrange it by taking the negative inside, then this bracket term will reverse. Cos theta 1 minus cos theta 2. Now in the case of potential energy, we need a reference point, initial point. So in this case we will fix the reference point as pi by 2, angle as pi by 2. Okay, so theta 1 is said to be pi by 2 and theta 2 is said to be theta. Okay, so this is the case. In this external field you are having a dipole. Initially you will fix the dipole like this, which is making an angle pi by 2. This theta is 90. Okay, isn't it? This is 90. Now after that you will assume that your dipole is rotated by an angle theta. Initially it is 90, then you will assume that from that 90 it is rotated by an angle theta. Okay, it is just for our convenience to set the reference point for potential energy. We will set like this. Now apply these values, then W will be equal to PE into cos theta 1. What is theta 1? Pi by 2 minus cos theta 2, it is theta. What is cos pi by 2? Cos 90 is 0 minus cos theta. This is minus PE cos theta. So you got W is equal to minus PE cos theta. You know that AB cos theta is equal to A dot B. So PE cos theta is P dot E and there is a negative sign. So you got W is equal to minus P dot E. This work done is stored as the potential energy of the dipole. Hence potential energy is equal to minus P dot E. This is PE is potential energy. Don't get confused. Left side PE is potential energy short term and right side minus P dot E, where small letter P is the dipole moment. You already know, electric dipole moment. E is the external electric field. Okay, so this is the expression for potential energy of a dipole in an external field. PE is equal to minus P dot E. So you got potential energy is equal to minus P dot E for a dipole. Now let us discuss the cases. First case, when theta is equal to 90 degree, you are having potential energy is equal to minus P dot E. that is equal to minus PE cos theta, that is equal to minus PE cos 90. Cos 90 is 0, so potential energy will be 0. So that is your reference point when theta is equal to 90 degree. Now when theta is equal to 0 degree, what will be the potential energy? Minus PE cos 0. What is cos 0? It is 1. So you will get minus PE, isn't it? This is the minimum potential energy. Minimum potential energy configuration is the stable configuration. So this is the stable configuration. How it will look like? You are having a field like this, and you are having a dipole with angle 0. Angle 0 means from here you are measuring the angle. This will be your minus q, this will be your plus q. Here you can see field and your dipole moment, both are in the same line, so angle is 0. Your dipole will be like this. In the first case, how is your dipole? Your dipole field is like this, and your dipole will be like this. It is making an angle 90 degree. Okay, now third case, when theta equal to 180 degree, potential energy is equal to minus PE cos 180. What is cos 180? It is minus 1. So minus PE into minus 1, that is PE. This is the maximum potential energy case, which is highly unstable configuration. And how it will look like? There will be a field like this, and your dipole will be like this. Plus q will be here and minus q will be here. In the initial case, you can see minus q is on left and plus q is on right, but here you can see that minus q is on right and plus q is on left. This is the difference. Here angle will be 180 degree, and this is highly unstable, so it will not happen. And any other angle, potential energy will be in between PE and minus PE, which is not maximum or minimum. In between some values you will get. So this is the case for potential energy of a dipole in an external field.